Last episode, we took apart the agent platform. Strip away the buzzwords, and it's really just a while loop spinning around a big model, calling it over and over, round after round. Which raises the obvious question. That model it keeps calling, how does it actually get served in the first place? This episode, we climb inside the heart of that loop. LLM Inference serving. Say the words inference serving, and a lot of people picture a ball of GPU black magic. Pseudokernels, tensor parallelism, spooky, mysterious stuff. Today, I'm going to crack that shell open for you. And you'll find there's no magic inside, just 4 old parts you already know. A batch scheduler, a cache, a fair queue, and a rate limiter. All wrapped around a single matrix multiply. Only one thing here is genuinely new. It's called continuous batching, and it's the first thing we'll dig into. First, lock in one fact that runs through this whole episode. A big model generates 1 token at a time, popping them out one by one. The technical word for it is autoregressive. To write the 10th word, it first has to have looked at the previous 9. To write the 11th, it looks back over all 10. That one property alone nails down every design decision that follows. Why can you do continuous batching? Because it goes token by token. The granularity is fine enough that the scheduler can reshuffle the deck every single token. Why do you absolutely need a cache? Because every new token has to look back at the text before it, and if you don't save that, you have to recompute it. Why does GPU memory become the bottleneck? Because the stuff you look back at has to sit there taking up space the entire time. 4 words. 1 token at a time. That's the key to this whole episode. One more division of labor to keep in your back pocket. Reading your prompt is called prefill. It swallows the whole input in one gulp. After that, spitting tokens back out one at a time is called decode. The first one hammers compute, the second one hammers memory bandwidth. 2 jobs with completely different temperaments. These 2 will come back to give us trouble later. Part 1, and the star of the show. Continuous batching. A GPU can hold a fixed number of requests at once. Let's call those slots. Say, 4 slots. The most naive approach is called static batching. You gather a batch of 4 requests and run them together, and you don't swap in the next batch until the longest request in this one finishes. Sounds fine. Here's the catch. In the same batch, one request is done after 5 tokens, while another needs to say 60. The short one is finished, but its slot can't leave. It has to sit and wait for the long one to grind out all 60 tokens. One slot spins idle for 50-some steps, and the GPU just sits there burning power, tagging along for nothing. Static batching wasn't dreamed up by some idiot. It's exactly how training works. A batch of data goes in nice, and even comes out nice and even. Totally natural. But inference is a different beast. How long each request will run, you have no idea in advance. The lengths can differ tenfold, and all of static batching's waste is hiding inside that uncertainty.
The symptom on your dashboards is textbook. GPU utilization is stuck dead at 40% and won't climb, while the latency panel is all red. The hardware clearly isn't full, yet users are stuck in the queue, waiting.
Continuous batching thinks about it differently. The instant a request finishes, its slot opens right up, the next one in the queue slides in, and the GPU never idles for a moment. I ran it with 12 requests, 285 decode steps total, on 4 slots.
Static batching takes 152 ticks to finish. GPU utilization only 47%. The slots sit empty more than half the time. Continuous batching needs just 85 ticks, and utilization jumps to 84%.
Same card, same amount of work. Throughput is nearly 80% faster, and tail latency drops straight from 152 down to 85. The key isn't that we swapped in a faster card. It's that we never let a single slot sit idle. And the reason it works comes entirely down to that phrase from a minute ago. 1 token at a time. The granularity is fine enough that you can repack the batch on every step. This is the single most central trick in frameworks like VLLM. You don't get to open as many slots as you feel like. What caps them is the second part, the KV cache. First, how much it's worth. Every time the model writes a new token, it has to look back at every token before it. If you don't store that, writing the ith token means recomputing attention over all I tokens from scratch. That's an I times I matrix, and the cost scales with I squared.
Generating 512 tokens. Without a cache, you compute over 44 million units. With the cache, only 130,000, 342 times faster. Generate 2,000 tokens, and the gap stretches to over 1,300 times.
So without a cache, long text is a total non-starter, and every framework stores this. But the cache isn't free. You cram the keys and values for every token, every layer, every request into GPU memory, and its size grows right along with context length and the number of requests.
For a 7 billion parameter model under plain multi-head attention, each token takes half a megabyte of memory, so one 2,000 token request is a full gig. Set aside 40 gigs for the cache, and you fit exactly 40 of them.
See that? That's exactly the slot count from before. The compute bottleneck just turned into a memory bottleneck. This is also why, the moment you crank concurrency up, the service OOMs and crashes. It's not that the math can't keep up. It's that the cache blew out the memory. Every extra long request you take on gnaws off another gig, and by the 41st one, pop. It crashes. A lot of people faceplant right here on their first deployment. They figure adding machines will carry it, when the real thing capping them is this memory. Good news is, there are tricks. One is called grouped query attention. It lets several heads share a single set of keys and values, shrinking the cache fourfold, so the same card fits 160 requests. The other is called paged attention. Like an operating system managing memory, it hands out pages on demand instead of reserving for the maximum 2,000 tokens right up front. In testing, that one move saves another fourfold. At the end of the day, in inference serving, managing memory is managing performance. Part 3, the fair queue. A GPU usually isn't yours alone. It's shared across a bunch of tenants. Tenant A is a chat interface. A few short requests, waiting on an instant reply. Tenant B is a batch job that dumps in 20 long requests all at once. If you've got just one first-come, first-served queue, B's 20 line up in front, and A's little request, the one that finishes in 4 steps, has to wait behind them until B is almost entirely done.
I ran it. First come, first served. Awaits 277 ticks on average, and the worst one waited 303. A 4-step job, waiting 75 times its own service time. That's what's called head-of-line blocking.
Switch to per-tenant fair scheduling, where every tenant still in the queue takes turns getting a freed-up slot.
It immediately drops to 19 on average, 33 at the worst. And B, it goes from 300 to 312, barely feels it.
A shared model service is, at its core, a fair queue. It's the exact same problem you hit in any multi-tenant system. Sticking the letters AI in front of it changes nothing about the math of scheduling. The fourth part, and the one that saves your life. Admission control. Slots are finite, but traffic doesn't care whether you have room. It comes anyway. Say 3 times what you can handle shows up. The most instinctive move is to take it all in. And the result? The queue gets longer and longer. Every request's latency shoots up, and in the end, everyone times out together. And if you keep forcing more in, the moment you go past memory, it just crashes. I took 120 requests and poured them in at 3 times capacity.
Except everything. All 120 do get finished, but only 16 were delivered inside the deadline. Nearly 90% is wasted, and tail latency spikes past 400.
Here's the nastier part. The users who time out don't quietly walk away. They retry. And those retries pour back in as new requests, piling even more onto the queue. The whole service falls into a death spiral called metastable failure. Even after the load drops back to normal, it can't pull itself out. Someone has to cut the traffic off before it can heal. You've definitely seen a service that, once it goes down, stays down for ages until a restart fixes it. 9 times out of 10, this is why.
Add admission control. It gates at the door. Admit only as many as it can process at once, reject the overflow on the spot, hand back a 429, and tell the client to come back a little later. The 44 it lets in are all delivered on time. The 76 it turns away fail in 1 millisecond and can retry, instead of leaving everyone to sit and wait 60 seconds.
The number you should actually be watching is called good put. The count of requests delivered on time goes from 16 up to 44, nearly 3 times better. Taking on work you can't finish just drags everyone down together. Saying no early is what protects the batch you can actually serve. This is just a rate limiter, the same idea as the back pressure you'd put on any overloaded service. Time to lay the honest card on the table. Take an LLM Inference service apart, and here's what it is. A continuous batching scheduler, plus a cache, plus a fair queue, plus a rate limiter, all wrapped around a single matrix multiply. The only genuinely new piece is continuous batching, and even that holds up only because generation happens 1 token at a time. Everything else is old craft you already know. The KV cache is a cache, and like every cache, it trades memory for compute. Until, trade after trade, memory itself becomes the bottleneck. Multi-tenancy is fair queuing. Overload protection is rate limiting. The model is the payload, and shipping that payload efficiently comes down to throughput, tail latency, memory budgets, and admission. Still the same toolkit from Season 1 and Season 2. A few last pitfalls. 1. Don't treat throughput as your only metric. What users actually feel is tail latency and time to first token. Open the batch too wide, and throughput looks great, but the first token actually comes back slower. 2. Prefill and decode are 2 different jobs. One eats compute, the other eats memory bandwidth. And scheduling them together makes them drag on each other, so plenty of frameworks now just run the 2 of them separately. 3. Continuous batching and a paged cache are great, but both of them are fighting memory fragmentation, so what you monitor should be cache hits and evictions, not just GPU utilization. Let's wrap up. This inference-serving machine has the model's forward pass dead center, and the ring around it is exactly the 4 old parts we took apart today. It's the heart of that agent platform loop, and every turn around the loop pounds on it. Next episode, we keep moving out toward the place the agent reaches into. We'll design a vector search system and see how its long-term memory actually gets stored and looked up. See you next episode.